Why are we interested in this relationship? Because once we identified it and we can design the material for the application we want. Like, for example, in my group, and we focus on the electronic devices and nuclear sensor and also the quantum computings. Okay, so first, what is the material science? And also, what is computational material science? And I really like one statement from my colleagues, Professor Amy Moore, and I think that some of you probably know her. And she said, like, anything is made out of something. So that something actually is materials. The performance of every device and machine in the world is limited by the properties of the material it is made of. So we always want the material better. So what does it mean better? Better, we want the material be stronger, tougher, more environmentally friendly, cheaper, corrosion resistant, like have a good corrosion resistant, also lightweight, right? And also easier to manufacture and have a better property than they used to have. Like you want, for example, you want your cell phone run faster, you want your computer run faster and can handle more data, etc. And so the basic solution for that is like, well, you have to have a better material, and then that can they can provide you a better performance or have a better properties, right, to accommodate or to meet your requirements. And or something, probably you come up with something, okay, some genius or something out of space or something very unique, like application you want your device to be able to do, and then that you still need to, okay, have something new properties, probably new material can meet your requirements. So usually, okay, we always require like a combination of all these features. And so it's make it like make the solution will become the more complicated. So it means like you need a more complicated material to satisfy the requirements. And so that's why we need a material scientist like to do this, to help us to find out the better materials. And the role of the material science is very simple, and I really like this figure. Actually, it just shows the relationships, and what we try to do in the material science is to find out the relationships for the process, structures, properties, and the performance of the materials. Okay, they all connected because they connected means that they all controlled each other's and to build up this like stable shape. And then the modeling and simulation, we're talking about like computational modeling and simulation, actually stay in the middle of this shape is to help this stabilize it, because we need to use this tool like modeling and simulation to help us to identify or to build up these relationships. And that's lead to, okay, we have another field, or I just want to say like a subfield in the material science, is called computational material science. And what is a computational material science? And the general definition for that is to use a computer, right, and to model and simulate material, and also to predict materials. And at the same time, actually, for the computational material science, and we also have to integrate different lengths and the time scale to fundamentally and essentially study materials. So you may ask, like, why do we need to care different lengths and different times, okay, for in the materials? So this example actually show you is like, okay, if we look at the different length scales, and this material will reveal and different properties. Like for example, this, okay, if we want to design a 1 meter size of the engine block for a car, okay? And then if we zoom in to the macro scale, and you will be able to see some grain, right? It's a little patch, right? Different color grains, and also be able to see the macro porosity. And then if you continue zoom into that material, and then you can see the microstructure, and then in the microstructure, you'll be able to see some microporosity or something dendrites, okay? And as you continue zooming down, we'll see nanostructure, and you'll be able to see like the precipitates. And at the end, okay, into very teeny, tiny small. and you'll be able to see atomic structure and also some interface and between the two structures. And all this different kind of structure will reveal variety of property, including like mechanical property, like the U strength, tensile strength, and also like thermal property, like thermal expansion, or electronic property if you go down to the atomic structure. And because the atomic structure can control the electronic property. So electronic property actually is the electrons, right? And so you need to zoom into the atomic structure and to control the electron flow. And so that's why we need the different length scale tools and to help us to see those different properties. And for the time scale is like, because we need to study and how the material grows or how the material degrades, and in probably femtosecond, picosecond, probably minutes, and or in the different hours or different years. And so that's why we need to use some tool to help us to simulate the materials and over time. And so this figures on the right here actually is to show you the different length scales and time scales of the computational tools and in the world now. So the very small one is called quantum mechanics. So we use a quantum mechanics, right? And to simulate something like the material down to atomic scale, and also can simulate some femtoseconds time scales. And then if we move up a little bit, and then we can use something called molecular dynamic, and you can see some like nanomaterials, and probably up to like, can see something like micro scale, like probably like up to some minutes, okay, for the molecular dynamics. And then mesoscale is to see the microstructures, and you can simulate some like thermodynamics based phenomenon of the materials. And finite elements and approach, and probably some of you probably familiar with, and this is like to solve the partial differential equation and for use to simulate the structural responses like probably over like hours or over years, and probably under like certain strength, and then so probably like under certain temperature or pressure, etc. And so you see different actually computational tools and can give you a variety of the material property to help you to review the variety of the material property or different like structures. Okay, so why do we need like artificial intelligence? So I want to kind of like go back to talk about some government programs. And so that's why the AI like step into the field. And back to 2008, the National Research Council actually released a statement. So they said, okay, integrating materials, computational tools, and informations with the sophisticated computational and analytical tools already in use in engineering fields, and it can promise to shorten the material development cycle from its current 10 to 20 years and to 2 or 3 years. So what does it mean, the material development cycle? Is like, okay, if you discover a material from the labs, and then you can successfully and synthesize it, okay, you know the property, you know the performance very well. Okay, after that, okay, it will take you probably up to 10 to 20 years and to introduce it to the marketplace. So the reason it takes such a long time because you have to go through all this complicated process. Okay, and then also you have to continue, validate your tool, you continue validate your material, make sure, okay, you can synthesize it or produce it in a very large scale to meet the market requirements. And so this is too long, okay, the government think. And then say, okay, why not we combine the computational tools and also information? At that time, we haven't really kind of like say, okay, we have to use machine learning or we to use some like AI. Just like, okay, combine the information and can we shorten this development and by 10 times? And then people think, wow, that's a pretty amazing. And so the first thing is that, okay, well, do we need the new tools, okay, to help us to do that? And so, and then move on to the 2011, okay, our federal government finally and come up with a white paper. And then they also announced a new initiative they call Material Genome Initiative, and it's also called like MGI. And they have a very clear statement. okay, for the goal of this MGI program is to accelerate the process to move a newly discovered advanced materials from the labs into the commercial marketplace and decrease the cost and time by 50%. They also have a very clear strategy how to do it. It's like, okay, I want all of your researchers, okay, the scientists to develop, oh, I'm sorry. Sorry about that. To develop the new tools and to develop a new integrated computational, experimental, and the data informatics tools. And so that's, they also identified as, okay, we have for this research, and we have to combine the experimental tools, computational tool, and some digital data tools. So up to that point, and we know, okay, this is the best time, that's the time, and we need to take a look at the AI. We need to take at any like AI tool, and we can include it and into our materials research. And so the next is I want to talk about, okay, why AI is needed in the field. And because, okay, up to like back to like centuries, and then actually we already have a large amount of material data, okay, available in the fields. And it's so difficult for us and to process the massive amount of the data. And also, so if we want to, and also we know, okay, the material become more complicated. And so that's why we need like spend more time on the experiments and computational modeling, and to actually to meet those requirements, to fabricate, like probably like to produce a new material to meet the requirements. And so it come up with, okay, if your requirements are too complicated, probably we have to take 10 years, 20 years, millions of years to make sure, okay, we can meet that requirement. And why not? But the point is like, how can we speed up this progress? And so that's why the material scientists are saying, okay, probably we need a new research method. So I put new here is because I know AI is not new. So, but for material scientists, actually, this is a new research method in the field. So that's why we need the AI, because it can help us to satisfy all the challenge and we are facing in the field. And the next is I'm going to demonstrate and some examples and how to show you like how the AI is integrated into the material research. Okay, so before I go into those examples, and I want to give you a heads up. And firstly is like, I'm not a data scientist, okay? I don't have a data science background. And I even haven't taken any data science course. So I cannot talk in a data science way. So that's sometimes like, will be kind of like have some language barrier and between me and also my data science collaborators. And because I don't have any background on that. And what I just know is the materials and also the computational modeling methods. And so this flow chart actually is actually this is the flow charts and I use and for my research. And so what I can provide for my data science collaborator is, okay, it's a material input data. Okay, I can provide you, okay, variety of the data you need. Maybe not the amount of data you need, but probably some data I can provide you. I can show you that like the example later, and you will know what I'm talking about. And I also am pretty clear is, okay, what I would like to see from this AI black box. So I would like to know the trend, okay, and also I would like to know the material selections. Okay, what material I need to select, and after running this like AI black box. And also, I want to see some new material. I hope the AI black box and can tell me. So the AI actually for me is a black box. So I don't know what the magic is. And so based on what I understanding, okay, so in the AI, in the material science, and we use machine learning is the most popular and the promising application of the AI. And this is how I see view the role of the machine learning and in the material science research. So firstly, okay, we need some experiments and or computational modeling to generate data. So a bunch of the materials data, and we will use some data to train the model, and then we will use another set of data to validate the model. After the model is validated, and then it will be able to make some predictions, right, for probably the data trends, and also can tell us, okay, what material we should select to meet the requirements, and also probably can recommend some new materials. And based on those outputs, but we still need to use like feedback, and to the very beginning, use experiments and computational modeling to validate and those predictions. And so I see this actually is a closed loop and in the research. Okay, so this closed loop actually of course, have benefits and also have limitations. And in the material science. So firstly, we know is, okay, if we apply this machine learning technique, it can greatly reduce the time. And so that's what we hoped. And we can quickly discover new material and also shorten that like material development cycle, right? By at least 10 times, I hope. And then second, but the point is like, if we have this machine learning, and that means we need more data, right? And to generate the data, and it's costly. And also, if you have just a very limited size of the data, and maybe will cause the error, and probably the error could be significant. And so this, the figure on the right actually show you, okay, if we increase the size of the training size, okay, for the models, and then the error will definitely can decrease exponentially. But unfortunately, okay, like for example, this here is we have like 100,000 data points. And this is very big for us for material science. And so probably for the computer science or for data science, and this is it's 100,000 data points is not much. But for us, that's a very unique case, and we can generate such a huge data. And most of the time, and for material science, and we only probably can generate hundreds, less than thousands, or probably even like just a tenth of the data points, and below like hundreds. And so that will be the drawback. And also that's I want to say the drawback is the challenge and for us, and to really merge like AI and into the material science and more effectively. And the other thing, the other challenge is like we know the machine learning or the AI on its own cannot create or discover new scientific significance. So that means that we still cannot just use machine learning, and we still need experiment. We still need the computational modeling and to help us. Okay, so it's kind of like, okay, we have the benefit, we have the limitation. How can we better use this, and how can we minimize the challenge, and then but still can use machine learning and effectively, and to help us to advance or facilitate our material science research. So here's as like a computational material scientist, this is how I see machine learning, the role in the machine learning in the material science research. So this is a triangle. I built out this triangle actually based on the time, accuracy, and also the cost. And the bottom of the triangle is machine learning. And then the middle part is a computational modeling. And then the top part is experiment. So if you start from the top part, we know, okay, we do need experimental data, right, to fit into our computational model. And then combine the experiment and computational model, and we can generate data and to fit to the machine learning model. And the machine learning model can generate more data for us, but it still needs the computation and also experiment to validate the model. So this is a kind of like a closed loop. And when we run it more and more, and of course, and it will make the models more accurate, right, more effective. And the last part is I want to show you some applications and of the machine learning and in the material research. And here, it's actually, there are variety, there are many, many types of applications. So here I just show you 3 types of application is because my research groups are very interested in. So the first one is accelerate computational simulation. Second, machine learning can help predict material structure, property, relationships. And then the third one is machine learning can effectively determine the parameter for a numerical model to predict the material properties. Okay, so the first one is to accelerate computational simulations. And like, for example, if I want to develop something called like interatomic potential for a large scale molecular dynamic, what is the interatomic potential? It's a mathematical function to calculate the potential energy of a system of atoms with a given position in space. So it sounds like very complicated. So now every time I tell my student, okay, if you see some potential, that means, okay, it's the interaction. So what we want actually is to study the interaction between the atoms at the like different position. Like, for example, the interaction between this like orange ball, this is the atom, okay? The orange and represent is a copper here, copper element. And then the red ball is an oxygen atom. And then the gray ball is a zinc. Okay, so if I want to study the interaction between the copper and the oxygens, or probably the interaction between the copper and the grays, okay? So, and then we can generate the potential. And why I'm interested in that is because in that way, and then it will help us to build up these materials, right? If we know the interaction between them. And so you see, well, seems like it's not difficult, right? But don't forget, okay, interaction is not just like one-to-one. You also need to like consider this one to another red, this one to another gray. And if we have millions of atoms, and that will become very, very time-consuming calculations. And so, and also, okay, not just the size of the atoms, okay, how many, like millions of atoms, we also want to see, okay, what happened if the atom moved over time, okay? It moved in a picosecond, or it moved in nanosecond, even move in hours. And so they will change their position, and then that means it will change their interactions. And so that will be very, very time consuming if we have to consider the calculation for individual interactions, okay, atomic interaction, we call it. And so that's why we think about this, okay, can we use machine learning to help us? And the material scientists, they say, find out, yeah, that could be. And so this is the matrix, and we generate for this system, okay? So the left one actually is the material scientist generates, okay? So for this system is like the copper and for the zinc oxide. And the left one is represent the coordinates. Okay, atomic coordinates means like which position the copper in, which position the oxygen in, and then which position the gray, like the zinc atom in. And then this will be the input. And then the input for the second line is represented, they call it symmetric function vectors. And this will describe the local atomic environment. So like, for example, what is the interaction between the gray ball and the orange, and the interaction between the red balls and the orange ball? And also, what about the interaction among the orange and the red and the gray balls, okay? And then the third lines actually represent is a neural network. So this is symmetric functions will generate a variety of vectors and use as an input and for the neural networks. And then after running the neural networks, and the neural network actually will generate the output for the atomic energies for the individual atoms. And when we combine them together, and that will be the interaction we're looking for. So if you want to know, okay, what is the neural network, and like what is the algorithm the neural network use, and then this is the equations and for the neural net to control the neural networks. And so you can see this figure here actually is to show you the neural network can generate that atomic interatomic potential pretty well. And when it compared to the traditional method we use is something called density functional theory, and which is atomic simulations, and to generate this potential normally we use, and then they match very well. And so, okay, actually that really helped. And so if you're interested in this approach, and please check out these papers, and they have more details about this paper will show you more details and about the neural network, how they set up that and how they run that, okay? And so that's one way and can use machine learning and in the material research. And then the other ones, and we can use machine learning and to help predict the material structure property relationships. And so what we expect is like the machine learning can help us to select the material quickly, and also help us to actually discover some new materials. And maybe we haven't like used like computational modeling or experiments and to synthesize it yet. And so this is another example, and actually this is another example in my groups and that we focus on, is called two-dimensional transition metal dichalcogenides. And the chemical formulas is MX2 material. So the M represent the transition metal. So if you remember, it's a chemical periodic table. And then in the middle part, there are a large amounts of the metal elements. So we call them transition metals. And so the M stand for the transition metal, and X here stand for the chalcogens. So chalcogens, it could be like a sulfur, seleniums, and also tellurium. So, so the purple actually atom represent the metals, and then the green atom represent the chalcogens elements. And so you can think about like for the transition metal, there are a variety of selection and you can try. And even for chalcogens, and then you can try like S, E, T, E, all those are the variety of elements. So they can form a variety of the materials, right? The two-dimensional transition metal dichalcogenides. And also we can combine the two types of this transition metal dichalcogenide together and to form something called lateral heterostructures. And so the left side composition and will be one type of the transition metal dichalcogenide, and then the right side and correspond to another type of the transition metal dichalcogenide. So you see there will be a lot of combination, and we can try with. And so why we interested in that, and because this type of material, and we can use it in the electronic devices, or probably can use in the net energy storage, like for example, probably use in the battery as well. And so the problem is like, okay, for the material question we have is, okay, for this lateral heterostructures, and we know if we change the left side and also, or the left side or the right side compositions, and then the material will change, means the property will change. And so we want to know, how does the type of the composition affect the structure stability of these materials? So the structure stability means like, okay, how strong and how stable they can exist in the world. And also the second question will be, how does the concentration of the composition, like for example, if I use like 10%, the left side composition, and then another 90% and will be the right side of the composition. Or if I increase or change the concentration between the two sides, and will it affect the structure stability? And so to answer these two questions, so our traditional way in the material science is, okay, we have to build up atomic structure, okay, build up some structure for each individual heterostructures. Okay, if we have like millions of heterostructure, and that means we have to create millions of atomic structures. And then for each individual structure, we have to run something called density functional theory calculation. So density functional theory actually is based on the quantum mechanics. So in that way, we can see like the individual atoms, okay, how they react, how they interact to each others. And then that will strongly affect the structure stabilities, okay? And so if we have millions of the potential heterostructure, that means we have to do millions of the density functional theory calculation. So, and then I thought, okay, let's, because this calculation is not difficult, it's very simple. And that's why I hire a material science undergraduate student to help me. And he spent 6 months on this project and only be able to look at 500 structures. And then he showed me figures like this. I said, oh, this is like a mess. Okay, I don't know how to analyze it. It's hardly see. Okay, so the y-axis actually to show something called formation energy, is the energy we need to use to form this structure. So if your energy is higher, like a more positive, that means it's more difficult. So more difficult, that means like that materials is not stable. And so what we want is like this formation energy will be more negative, and then that will be better. So that means it will be easier to form in the nature. Okay, so and then also that means it's more stable in the nature. And so he screened, okay, 500 heterostructures and using like 6 months. And I said, okay, we seems like still have a lot of structure we still need to look at. So he came up with, okay, another questions I have is, how could I speed up the project progress to screen all possible heterostructure? Because at that time, I didn't know how many possible structure I need to study. And then the second question was, how could I quickly and accurately identify a group of a heterostructure to focus on from this like a vast amount of the candidate material? Like for example, if the student gave me this, I said, how can I identify which one I should focus on? So that's a that's kind of like made me think of, okay, probably I need some new methods. And so we think about, okay, machine learning. And this is a figure actually to show the comparison and how can we integrate or combine the density functional theory calculation, okay, we use, and to calculate that formation energy and with the machine learning. So like I say, for the density functional theory, the input is the atomic coordinate. We need to build up the structure one by one. If we have millions of the structure, we have to build 1,000,000 structures. We need to get the coordinate for each structure and use that as input and put it into this density functional theory tool. And this tool actually is to calculate this equation, very simple. It's called Schrodinger equation. And so once we solve out this equation, and then we can put out the property we are interested in, okay? And then, so machine learning, we know is a difference. So we don't need to build up the structure, okay, one by one. We can just like tell the machine learning model some structure features. Like for example, we can tell it the composition, the type of composition, or the concentration of the composition. Those are the two things I'm very interested in, because I know they will actually affect the structure stability. And I can also add some like other physical features or chemical features, and I'm interested, and use them as the input. And then put it into a machine learning box. So my student told me, oh yeah, we can try like kernel-ridge regressions models and use those like structure feature as the input. And at the end, okay, the output will be the formation energies. And so in our research, and we still need definitely at the very beginning, because we need to train this model, right? And so we still need some data from this density functional theory. And so we will use the 500, the data set, the data points, and we already generated from the density functional theory calculation, and use it as the input and to train and validate the model. And then we can use this model to predict some new formation energy, and we haven't calculated yet. And so that will help us to identify, also find some new candidate as well. Okay, so that is the approach and we used. Okay, so this is the results and we got. And like I said, the structure feature will be the input for the machine learning. And so at this point, we don't know, okay, what structure feature we should use. So we try a variety combination for the structure features as the inputs. So we try like different, this like single pairs and triplets, it just like refer to the concentrations and for the different composition. And we also start to add some physical features, some kind of like a physics in there. Like for example, average like atomic weight, or we also add some negativities, and also like atomic weight difference, or any like the individual composition formation energy. So that means like if I have a separate, like we want to focus on this heterostructure, if we separate them, and what is the formation energy for the left side composition? What is the formation energy for the right side composition? And then what happens if we include all those structure features? And this is the figure actually to show you the formation energy predicted from the machine learning, and also the formation energy and calculated from the density function theory. And we also determine this R2 term, and R2 is the coefficient of the determinations. And we see actually it changed and gradually and based on the structure features. And the other very interesting thing we want to know is what is the controlling features. So it means that, okay, which feature here would be the most important and to control this formation energy. And then from the machine learning, and then we find out, oh, the individual composition formation energy and will be very important. So you may say, well, why is it important? Because this will help us to identify which materials, quickly identify which material and we should focus on. And before we need to run any calculation, or before we need to like synthesize the materials in the experiment, in the labs, okay? And so the next like goal we want to meet actually from this machine learning research is like, I want this machine learning model to help us to predict more formation energy. It means I predict more new materials, and we haven't calculated using the DFT, using the density function theory. And so the machine learning actually can quickly screen the formation energy for over like 1,300 heterostructures. So think about like, we need to spend 6 months and to get the formation energy for 500 structure. And machine learning actually can just spend 2 hours, I think probably less than 2 hours, to give us the data and for 1,300. And so that is really, really amazing for us and to us, like when we saw this data. And then also this is just like some of the data and generated from machine learning. And you can see actually the formation energy, and some formation energy is negative. Like I said at the very beginning, you say, okay, we want to identify the structure and which can give us the negative formation energy. So like, for example, this two, and then we can quickly just pick up, oh, okay, we should focus on this two and materials. And then we could suggest to our experimental collaborator and then to synthesize them. And so that will actually really help us save a lot of time, and also will help us to like find out the area or the material and we should focus on. And yeah, so the machine learning actually is very good, I mean, for this example. And another examples, and we use the machine learning, is to predict another type of property called molar absorbance of the die, and we use a machine learning for quantum computing. So this property actually is to measure how well a die absorbs light at a given wavelength. So what we want is like, we want to identify the die, so something like this. So this is a chemical molecules, right? This, if we shine a light on this molecule, and then it will give us a strong, like a high molar absorbance coefficients. So the higher will be better. So it means like they were more sensitive to the to the light. And so we have two questions, and we hope the machine learning can help us. And one is like, what is the die structure and molar absorbance relationships? And then the second question is, which groups of the dyes can provide a high molar absorbance coefficients? And of course, I mean, we can use a computation modeling to calculate them, but it will take time, like I say. And so we kind of like, we also want the machine learning can help us to identify, okay, which structure feature can control this coefficients and can give us a higher coefficient if the material have that specific structure feature identified by the machine learning. And so in our study, and we try different structures. And so we try different combination. Like for example, we say, okay, what about we consider the number of the carbon, the number of hydrogen, number of nitrogens, and also the number of different like functional groups, and also the conjugation length, etc. Okay, what is the R2 will be, and for the machine learning models, and we used, and then we see if we change the structure features, and actually the R2 will be affected, will impact as well. And at the end, and we select this structure features, it just like consider the number of the different species or different elements. The reason for that is like, because the number of the elements, and you can easily find from the database. So for the number of the different functional group, like the benzene ring SO3 functional group, and most of the times, actually, we have to do it manually. We have to like take a look at the molecule and then calculate, okay, how many SO3 and that functional group in that molecules. And so we want to do it like quicker. So we don't want to, okay, if we can use a machine to help us to identify that quickly, and that will be better. And then the second thing is like, if we only include the number of the different elements, and we will be able to find more data and in literatures. And so, and that will increase the size of the training set. And so that's back to what I showed you a few minutes ago, a few slides before. It's like, if we increase the training set, right, we increase the size of the data to train the model, and then the error can slim down. And so here, actually, because we just, this is actually it's a preliminary result, we only have 100 data sets. It's not much. And so that's why you see the R2 actually is just like a 64%. But for our up-to-date research, and we already found the data up to like, I think more than 300 data points. And this value is dramatically increased. I think it's close to 75% now. And also, the machine learning can help us to identify actually the number of the carbon and the number of the oxygens are the two potential key controlling factors, and for this molar absorbance coefficients. And so those are the very important information, and for the material scientists like me. And then because we can quickly identify, if we know, okay, more carbon will be better, and then I can quickly find out, okay, which dye and which chemical molecule will have a more carbon, and I think I can focus on that. So I don't need to do all the calculation for hundreds of the different dyes. Okay, so, and the last application, and I want to show you, is called effective determinants parameters, and for the numerical models, and to predict the materials properties. And so this is the model, and can use and to help us to study organic the molecular semiconductors. And this study actually is to use two types of the machine learning model. One is something called the kernel-rich regression, KRR, with the Gaussian the kernel, and also the neural network, NN. And they use this two model and to predict like two important property. One is called the excitation energy, and then the other one is called excitonics couplings. And because once we get those two parameters, and then we can derive there's something called like Franco-Hamiltonian from the Hankel-Hamiltonians, and then we can extract some excited state property of the system. So you see this actually material is very complicated, and that actually consists, I think include more than 300 of these like chemical molecules, and then they arrange in the random orientations. And so this two parameter actually is controlled by the interaction between the two individuals molecules and chemical molecule. So you need to take a look at, okay, what is the interaction between this molecule and that molecule, interaction between this molecule and that molecule, and then we can use those interaction and to derive equation for these two parameters. And so you can think this is a really time-consuming calculation as well. And so actually this study and use this flowchart and to quickly can get the information and from the machine learning model. And the first one is, okay, to run the sum like 10 picoseconds and using the molecular dynamics, something tools, and then to generate the coordinates and for the individual molecules. And then they can put into this matrix, it's called Coulomb matrix, and this will be the input for the machine learning model. The output will be excitation energies, and also another output is called excitonics couplings values. And so the first one is to use a KRR. And so like I say, the input is this Coulomb matrix, and based on the coordinates, the output is the excitation energies. And then also could use the neural network. And the reason to use a neural network here is because the data point actually have more, and we also the people expect, oh, okay, have a more larger data points, and so have more data points, and probably the neural network can work better. So here you just want to test it. Okay, if we use the neural networks and also the KRR, which one can give us more accurate results? And so this flowchart show actually is, if we use neural network, okay, the input is the Coulomb matrix, and the output for the neural network is this excitonics coupling coefficients. And what will be the errors will be, what the error will be. And then if we change this, okay, use the KRR, another type of the machine learning, okay, the input is still the Coulomb matrix, and the output and change it to some of the parameter, we call it here is a transition dipole, and then use this transition dipole, put it into this equation, and then we can get this excitonics coupling coefficients. And what will be the error? What the errors will be? So compared to our traditional calculations. And so this is the result, and you can see, and if we use a KRR models and to predict this excitation energy, and if we have the training set is larger, and then the errors will dramatically decrease. So it works very well. But for using neural network, okay, this is called like direct method. Means like it's used. We use this. We have the Coulomb matrix input and directly output this excitonics coupling coefficients, and so it's called direct method. And the error, yeah, decrease, but not dramatically compared to this indirect method, and which is use like KRR. And so the indirect method is like use a KRR to calculate one of the parameters. So this is called transition dipoles parameter, and then put it back to that excitonics coupling equation and get the final results. And so here, this figure actually show you actually this indirect method and show actually work better because the error can dramatically decrease. And so this is something actually give us some thought is, okay, the data size is really also not just affect the errors or affect the final result, will also affect, okay, what model, what machine learning model, and what method, and you should use. You should use like neural network or KRR, etc. So here is like the finals. I want to kind of like summarize some of the challenge actually we've seen and in the AI and use in the material science research. The first thing, like I showed you in the previous example, is a data. Okay, the material science data is still too small. We know that, but unfortunately, that's the case. And it's very difficult for us to to provide millions or trillions of the data sets. We know, okay, you have more data is better, but every data we get, and we have to run the calculation, and we also have to do the experiment to fabricate, to provide those data. So every data is time consuming. That's why we always have a small data. And also another problem is like for the material science, the data doesn't have standard. So it could be different type of formats or we use a different type of symbols. Okay, even like, for example, for some energy, sometimes we use A, sometimes we probably use F symbols. So or probably sometimes we use P symbol, sometimes we use E symbol to represent the same energy definitions, the same energy. Yeah, so the terminology could be the same, but symbol could be different. So it will be difficult, probably like for the AI. And also a lot of data are not public. They are not public. And it's more like in the privates. And yeah, you can require probably the researcher to release the data, but it takes time, and probably they will not release all of them. So that's kind of like cause the data problem. And how can we actually find a solution, and for our material science actually, and to have a better use the AI. So I'm still thinking about it, and I'm also welcome to the discussion as well. And the second challenge I see is how can we better merge the AI and the material science? And so that means like, how can the AI and material science people talk in a more effective way? I see this is a problem always happen at the very beginning of the research. And because we know material science, we know, okay, what we can provide, what we're looking for. But how AI can better help us. And so AI probably have like a black box for us is, okay, they have different tools, but how can you click those AI tool and to the material science research better? And that will take some time. So there's also a challenge. So I'm thinking is it necessary to train each other on some level? So I'm not expecting like the AI people become a material scientist, or material scientists can become an AI scientist, like so that we can talk. And so here I show the two figures, and I see how it works. How can better merge the AI and MS? Is like for the research is not MS plus AI, and then we will be able to get the products. So if we work in this way, it always work parallel. So because that was hard to, there's no communication. So I see the merge is like, we should work in this way. And then we can find out some common area. And then after we find out common area, and then we will be productive and we can work out something. So some common area, I mean, is like, for example, we understand and what we're talking about. Like, for example, if I want my collaborator to calculate, hey, can you use a machine learning model to help me to calculate the formation energies? And so I need to explain to my AI collaborator, what does it mean, formation energy? What formation energy I'm looking for, and why that's important? Okay, what is a potential like structure feature will be important and to control, and this formation energy, because all those information and could help the AI collaborator to build up the model and also build up the database, probably data set, like input data sets, and for the machine learning models. So that's something I have been still thinking and also want to probably discuss with all of you. And if you can give us some suggestion, and that would be great. Okay, so here is the lessons, and I would like to share some lessons and I have learned, and based on the research and I have done. So I know that, and also this is the lesson, and my AI collaborator told me always is that AI is not a magic. So that box is a black box for us, but it's not a magic box. It's not always like can turn out something new, or something like not always like cannot give us anything we want all the time. And so we have to be realistic. And then the second, AI can help arguments your computational models by accelerating the number of the data points and you can exams. So I already showed that in our formation energy example, and also pointing you towards a new scientific significance. Like for example, can help us to identify what is the controlling factor and for specific properties, and can expose things, can expose like a new collaboration and the trends in the data. And so can help us to find out the structure and property relationships. And so those are very important. Some warning side is like, if the model are too good to be true, and you have probably overtrained them. So we should not just look at the R2. Okay, because for the material scientists, we always think, okay, if the R2 equal to 100, that means the best. So my AI collaborator tells me, nope, it doesn't mean that so that means that you overtrain it. And then the second, your model are fluid and ever changing and evolving with the more you learn. So it means like you train it more, actually you run that loop, the closed loop more, and then your model will become better, more effective. And so that's what the lessons and I have learned so far. And so at the end, and I would like to thank our funding agents and also my materials theory and modeling team, and also my collaborators and from the experiment side, and then they provide the data for us. And so if you're interested, I want to do some promotion here. If you're interested in join the team, join our work. So especially I show you that the dye screening for the quantum computing to calculate that molar absorbance coefficient, it's just like preliminary result. And I have a position open for that. So I really hope I can hire one student and with the data science background. And if you already took like intro to data science or intro to machine learning, and feel free to contact me. And it is a paid job, definitely. And so what you can expect, the first thing you will learn definitely some organic chemistry. So you will learn how can you use a data science and to leverage to help like organic chemistry research. And of course, you will be able to learn material science and also will be able to learn computational modeling, and you will closely work with our AI collaborator. So you will strengthen your machine learning backgrounds and also programming backgrounds. And also you will have an experience to work with the experimental and computational people in different scientific and engineering backgrounds. So we have a physics people, we have a chemistry people, we have material science people, we have electrical engineering people, and all work in this team. So if you're interested in that, and please send your CV to me. And I think that's it. Donna.
Okay, well, thank you very much. I guess this is the part where we clap.
Thank you.
And everybody can do, let's see here, I think it's that.